Presently working as an assistant professor at Computer Science Department in IIT Kanpur. He did his PhD from Saarland University in Germany with specialization in natural process learning. Other areas of interest are machine learning, statistical learning, deep learning, and artificial intelligence. The topic today on which he will be speaking is just a minute. It's effective computing, a multi-model approach. Dr. Modi? So can you hear me?
Yeah, I can hear you. You can hear me?
So please, we can hear you. Okay. So please start.
Thank you. Okay. Thanks a lot. I will just start sharing my screen. Just give me a second. So I hope you can see my screen. All right. Okay. So so let me just a second. Yeah. So I hope everyone can see my screen, right? My screen is visible?
Yes, sir.
Yes, sir. Okay. All right. Okay. Let's start. All right. Okay. Thanks a lot for inviting me for the talk. And and thanks a lot for the introduction. As Dr. Namita mentioned, I am assistant professor at the Computer Science Department at IIT Kanpur. And today I'm going to talk about something called affective computing. And then, you'll get to know what exactly affective computing is during the talk. So let me get started right away. So before I actually go into the details of the topic of the presentation, I would start with some technical background, as some of you are new to the area of deep learning. So I'm going to give a very brief overview of the deep learning and different architectures that are currently being in use. And then I'm going to move on. Once I've done that brief introduction or kind of a crash course, then I'm going to move to what exactly is affect and why should we care about affective computing. And then I'm going to talk about why should we care about multi-model effect. And then finally, I'm going to tell about emotion prediction. Basically, affect is about predicting the emotions. And then I'm going to talk about two of our recent works. One is predicting the emotions by modeling the emotion definitions, and then another one by modeling the emotion shifts. So I'm going to get into details later. And then finally, another aspect of affective computing is generation. So I'm going to talk about how to generate text which has emotional flavor to it. So let me get started with it's kind of a crash course on deep learning. And deep learning is very vast. You need a full semester of course to understand everything, but I'm going to cover in a very short duration of time. So it's going to be kind of a high-level overview. So I'm going to skip many of the details. But if you have any questions, please feel free to ask. So the way I look at the entire prediction framework is as follows. So you're given some, let's say you're given some input X, and then what you want to do is you want to predict some output Y. And this output Y could be either some kind of label or maybe some kind of a regression value or some kind of real value. So for example, X might be, let's say, a text, like one sentence. And then you want to, let's say, predict whether the sentence has a positive sentiment or does it have a negative sentiment, right? So the typical framework that is used is, given input X, you extract certain features from this input X. And then once these features are kind of something which will help in predicting the output Y. So these are kind of distinguishing things which will predict the output Y. And then once you have extracted these features, you pass it through a model, which I've written by phi here. And theta are the parameters of this model. So you pass it into a model which takes these features and then predicts an output Y hat. So this output y hat may not be same as the true output that you actually desire. And so what typically happens is that you compare this y hat with y, and then via some kind of a loss function which measures how much is the discrepancy between the output y hat and y, and that provides a kind of a feedback to the model to adjust its parameter theta so that the output y hat comes closer to y. So it's the framework is kind of simple, where the loss function is measuring the discrepancy between what model has predicted and what actually is required to predict it, and it is providing a signal to the model itself to correct its prediction by adjusting the parameters theta, right? So that's the general framework for prediction. And so typically these features that you see here are, you saw this feature extractor, right? So these features that you see here are, typically they had been hand engineered or extracted using certain feature extractors. So what that means is that there's a human involved there, typically an expert in that area for which you are doing the predictions. So they will extract some relevant features from the input, or they will write some code or some feature extractors to extract the features from the input. And these extracted features are typically represented in form of, let's say, a vector, and these are fed into the model. But then there is a lot of problem with this approach. What happens is that this feature engineering is a manual effort. So of course, it's a lot of time consuming and laborious effort. And also it is prone to errors. So it might, since a human is involved, it might happen that they might miss certain important features, or they might create certain redundant features. So all sorts of things can happen. And if your features are not good, then the model will, of course, obviously not make a good prediction here, basically, right? So because what model does is it is making the prediction on the basis of the features that are fed into it, basically, right? So that's the traditional approach which has been used for, let's say, classical machine learning. Another alternate approach which has come into limelight recent in the past, let's say a decade or so, is like learning these features automatically from the data itself. So what you could do is here what you could do is you make the feature extractor itself the part of the model itself. So what you feed into the model is the raw input X, and then the model extracts the relevant features and then makes the prediction. So there's no human involved in this thing. So the model directly extract the relevant features which are important for the prediction. So here, and this is what actually happens in deep learning. So basically, the deep learning, you feed in some input X, and the relevant features are extracted from the neural network model itself. And these features are, it's an automated process, so there's no, human involved, so it's not laborious and it's less prone to error because these features are going to be tuned to the desired output, basically. Right? So that's what the deep learning models are really good at, extracting the features automatically. But and going further, what can be done is that these features, instead of extracting just one feature, like one feature vector, you could extract a hierarchy of features. So like, for example, at the lower level, you could have, suppose this input is an image. So at the lower level, you could have features like which tell about the different edges in the image. And then at the next level, you could have some kind of shapes, geometrical shapes in the image. And going forward, at the highest level, for example, you might have some of the objects or the semantics of the image itself, basically. So basically, so there are these representations which are learned, and there is a hierarchy of representation. And once you have these features, you feed it into a regular your classifier or the prediction model, right? So, but the important thing to note here is that the loss function is actually helping in learning the features itself, basically. And the loss function is helping. So basically, you're learning the features from the data itself, and the loss function is aiding that basically, right? So loss function is guiding the feature extraction process itself because it is measuring the discrepancy between output to output and the predicted output, and it says, oh, this is let's say differing by let's say 100. So you need to adjust the features accordingly so that it comes closer to the true output basically, right? So everything is, so this is what is called like kind of end-to-end learning. So everything is learned from data itself. You just feed in the raw input and then you're getting the output, the predicted output, right? So that's the general framework, prediction framework. So I'll quickly go through. I think some of these would have been covered in the previous lectures in the workshop. So I'll very quickly go through some of the deep learning architectures or the neural network architectures. So what I'm going to talk about is this model essentially. What this model theta, this model phi can be basically. So one of the simplest model is like a perceptron. So the idea is very simple here. Like you have some input features x1 to xn, then you weigh them with different weights w1 to wn, and then you take a kind of a weighted sum of these along with some bias, and then you pass it through a nonlinear function g. So I mean, this is how you compactly can write it. And then yeah, this is in more in like vector and matrix notation. And so once you do that, then you make a prediction y basically, right? From this, you take a weighted combination of the input features, and then you make a prediction y, right? So, and what is really important is this g, which is the nonlinear function, and this is a nonlinear activation function. It is called as, and there are like different kinds of activation functions which have been introduced. So, like for example, sigmoid, hyperbolic tangent. So, sigmoid, for example, is something like this, and hyperbolic tangent might be something like this. So there are different nonlinear activation functions, and each one of them has its own advantages and disadvantages. So, for example, one of the most popular ones is this ReLU, which is basically zero if it is less than if the input is less than zero. Otherwise, it is same as the input. So this one basically. Right. So, I mean, I'm not going into details of the advantages and the disadvantage of different activation functions. I mean, otherwise it'll take. It'll take the entire lecture because it's quite vast. So I just discussed was a single kind of a computational unit which is called a perceptron, which takes in a weighted sum of the inputs. But what you could do is you could be a little smarter and kind of combine these different perceptrons. So, for example, you have one perceptron here. You take a weighted sum of these. I've represented it by a matrix. Excuse me. And then you take another perceptron, and then again the weighted sum, and then similarly other perceptrons as well, basically, right? So the idea is that you combine different multiple perceptrons basically, right, with different weights, and these weight vectors are different, and you combine them, and then you get some activations like y1, y2, y3, and y4, and y like that basically. And then what you could do is you combine another layer of perceptron. So this is like the first layer, let's say, and this is the second layer of perceptron. And then and so you can go on so on and so forth. And I think there's some problem in my internet. Just a second. I'm just rejoining.
Yes, sir. Okay.
Yeah, sorry for that. Some problem in the internet. Okay, so am I audible?
Yes.
Yes, sir.
Okay, okay. All right, okay. Yeah. So, yeah, basically, as I was saying, that you can combine, different layers, and then you can get these outputs. And mathematically, this is how you are doing. Basically, this is like a single, there's a layer of perceptron. Earlier, we had just one perceptron, but this is a layer of perceptron. So, X is basically a vector here, or maybe actually a matrix, depending on how you see how you arrange it. And similarly, you have different hidden representations. I mean, these H are called a hidden representation. So intermediate representations that are learned. So as I explained earlier, these are like different intermediate features that are being learned basically. And then you get some output Y basically. Right? Yeah, so this is also called as two hidden layer because we saw there are two hidden layers. And now what is important is the loss function. So as we saw that in the generalized architecture, that there is a loss function which measures the discrepancy between the predicted output y hat and the true output y. So this loss is, I mean, basically you have this loss L theta, and this is over all the training examples that you have. And then you do some kind of regularization over this thing. And theta are the parameters of the model, basically, right? So you basically want to minimize this loss function, basically, right? And then you learn the parameters theta, which will tell what to predict by using gradient descent algorithm and backpropagation. Right. So I'm actually not going into any details here because I mean this will take a course on its own basically. But I mean the general idea is that you have some kind of a gradient descent based algorithm and backpropagation to learn the parameters. So so I think in your some of your previous lectures you learned about convolutional neural networks (CNNs) and then feed forward neural networks, which I just spoke about, like the this one basically. Multi-layer perceptron. This is kind of a feed-forward neural network. So this feed-forward neural network. So these are essentially feature extractors, right? So they take an input sequence and extract relevant pieces of information and represent it as a vector, basically, right? So basically, they extract the features. These represented as a vector, and this goes to a predictor, and this predictor is typically a MLP or multi-layer perceptron, which we just saw, basically, right? And as I said earlier, also good thing is that everything is trained end to end. So the loss function helps to learn these features and these parameters as well, basically, and this final representation, right? So essentially, these CNN feed-forward neural network and recurrent neural network are essentially kind of building blocks. You can combine them in different ways, and then you can create really complicated networks, basically. Right. So let's look at an example of a feed-forward neural network, how it would do prediction. So here I have I have a task of predicting, let's say, the sentiment of this sentence. So for example, I have sentence "I love chocolate." And I want to predict whether it's a positive sentence or is it a negative sentence, or is it a neutral sentence, basically, right? So the way you could do this is as follows. So you first break the sentence into words, like this is called as tokenization. So you have I, love, and then chocolate. And then what you do is you maintain a matrix which basically learns where each row of the matrix is a representation for a word. It's a vector representation for a word which captures the properties of the word, basically. So what you do is you have some kind of vocabulary V, this one basically, and this vocabulary is all the possible words that could be there in your corpus, brain corpus, basically. So what you do is, for every word you have an index, let's say 1 to 10, so on and so forth. And these index is basically the index in the matrix, embedding matrix, this one, E, basically. Right, so every word corresponds to a row in this matrix, and each row is learning the properties of the word, like what kind of word it is it a noun, verb, what kind of meaning does it have, on all those kind of things, basically. So once you have that, what you do is you feed in your sentence, tokenize it, and then for every word in this sentence, you get the feature, this vector. So this, as I said, like each row is a feature or the properties of the word, feature vector. So you get this feature vector for each. So here we have 3 words, so you get 3 feature vectors, like for one for I, one for love, and one for chocolate. And then you take these feature vector and take the average of these feature vector, and then you get the final feature vector. And then you feed into the network, which predicts whether it's a positive, is it a positive or a negative sentiment, basically. Right, so this is how and this is called as continuous bag of words, because you're ignoring the order of the words in this. You just take the words and take their features and then take the average of these. I mean, I could change the order of I could write like say chocolate, love, I, still the vector is going, this final vector is going to be same, basically. Right, so so this is like a bag of words. Right, so and that's how you are making a prediction. Any questions on this? Any questions so far? All right, so yeah, so that's the like a simple feed-forward neural network for making kind of a sentiment prediction for a sentence. So this embedding, so now the important thing to note here is that, I mean, how do we get these representations or the features for these different words or the properties of different words? So as I explained earlier, there is a loss function which kind of guides the entire network and helps to learn these representations or the embeddings. Each row is called an embedding, basically, right? So these are also called as word embeddings, basically. Right, so these word embeddings are learned from the loss, with the help of the loss function, basically. So once you have trained this network, you have learned the properties of each and every word, basically. Right. So so as I said, like the disadvantage of this kind of architecture is that ignores the ordering information. So if I have sentence, it was not good, it was actually bad, right? So this has a negative sentiment. But if I say it was not bad, it was actually, it's a positive sentence. So if you can see, the words are same in this, both the sentences, but the order is different and the meaning changes. So, but this model SIBO, which I call, kind of ignores that. So it will be making the same prediction for both, which is incorrect. Right. So I think what is really required is we need to make use of some kind of ordering information there, basically, right? So that's where these RNN or recurrent neural networks come into picture. So basically, RNN capture the patterns in the long sequence. So for example, in a sentence, paragraph, or document, and they basically extract the task-specific information and summarize it in form of vector. So you have a long sequence, and it will extract the information from this each and every word, and then summarize it as a final vector, basically, which is relevant for the task. And so as opposed to classical models like hidden Markov models or maximum entropy Markov models, these do not have any limitation with respect to the amount of history it can deal with. Essentially, they have infinite, they can work with infinite history basically, right? And then they can also be used for purpose of generation, as I will show a little later. So the idea behind recurrent neural networks is very simple. So we have some vectors, let's say E1 to EI. So what RNN does is it takes in these vectors and summarizes the information so far in form of YI, basically. Right, so it takes vector from 1 to I and then summarizes to give YI, which is this output. And if you have a sequence of length n, then it summarizes to give the output yn, right? So I mean, more like maybe with the help of a diagram, you can see like you have some word w till wn, right? So for every word, you pass it through an embedding matrix. We saw the embedding matrix earlier, right? So you have this embedding matrix. And then for this word, you will get some index. From this index, you get this E1 basically, right? So this E1 is fed into the RNN. And this RNN gives certain, it could give certain output Y1 or it could not. I mean, depends on the task. And then it does it for every word. So this YN is the summary of the entire sentence basically, which has n words, right? So that is what this RNN is doing, right? Any questions on this? All right, so more mathematically, what is happening is as follows. So you have this word WI, you use this WI to get an embedding for this word small ei, right? And this embedding goes as input to this RNN cell, R basically. And this RNN cell maintains a hidden state, H basically, this H. And so this hidden state is capturing the information so far it has seen in the sequence, right? So basically what
Excuse me, sir.
Yeah.
Sir, every word is predefined in this RNN.
Predefined as in, what do you mean by predefined? Hello?
Yes, sir. Sir,
So,
every time we just, like you said that, na, ki, if we write the sentence where there is some different meaning, but the output is always same by this system. So every word has predefined itself.
So basically, see, depending on the see the predefine. So what you have is this this sentence, right? So sentence can be different, basically, right? So depending on the
always E has the same value, same output for any sentences.
No, for every word you mean, right? So E, this small
yes,
E you
sir,
mean?
Yes, sir.
So basically that's a good question. So basically this what we are doing is this initially what we do is this embedding matrix we don't know the feature vector for every word basically, right? So we are not aware of. So what you do is you initialize it randomly and then you learn it during the training itself. So this E1 is also learned during training itself. So it is not fixed. It is changing with training basically. But once you have trained your model, it becomes fixed. So representation, so it's like you are extracting certain features for a word. And then once you have extracted those features, then you fix it basically. Because I mean, those features will be defining that word basically, right? So it's like understanding the meaning of that word basically.
Okay, sir. So we have to try all the possible test cases on this.
No, so basically you train it all possible. Sorry, what?
Sir, we have to define all the types of test cases. मतलब पहले से ही हमें सारे के सारे टेस्ट डिसाइड करने पड़ेंगे. मतलब
I mean, you would have to decide all the training cases, you mean, right? Training, you mean?
Yes, sir.
So you will. So in order to catch all the possible meanings of this word, yes, you will have to define lots of different training cases, right? And that's why if you have lots and lots of sentences, then you will get a better meaning of the word, basically.
Okay,
All
sir.
right.
Thank you.
Okay. Any other question? Okay. All right. So then, yeah, as I was saying that you have so mathematically, what is happening is, yeah. So this you have this hidden state which is maintained by this RNN, and this hidden state is capturing the information so far it has seen, basically, right? And basically the RNN is taking the input, this embedding along with the current, the hidden state, this one basically, and then it is producing the next hidden state, which is kind of updating the hidden state because you have new information here, and also making a prediction, this yi that you see here basically. And so this, this RNN also has certain parameters theta basically, right? So which are getting updated every time it gets a new input and the hidden state. And this yi is predicted with the help of this another function O, which is parameterized by this phi2 basically. And this RNN R is parameterized by phi1 basically, right? So mathematically, this is what is happening. Like it is taking hi minus one, the previous hidden state and the current input, and then updating the hidden state. And similarly, you can make the output yi given on the current hidden state, right? So that's how the RNN is working. And you can also kind of represent it more kind of in a different notation. So this hi is basically becoming the hi minus one for the next step, basically, right? So you can see there's this recurrence relation. Recurrence is happening. So that's why this R in the RNN basically. Right. So that's the kind of the architecture that is there. So maybe let's also look at the RNN in work. How does it work, right? So initially we will be given some hidden state h0. This might be some random value, or it might be taken 0 as well. I mean, it's a vector of 0 values. And then what you do is you get some word W1. Suppose we are making a prediction, the sentiment classification, for example, whether a given sentence is positive or negative. So then you make a prediction, you take this word W1 and then you pass it through the embedding matrix to get this E1, right? And then you pass it through the RNN. And then you get the updated hidden state h1, right? And then if you want to make a prediction at every word level, then you do y1, otherwise you just go forward. And then similarly you get next word w2, and then you make y2 and h2 you get h2 gets updated here, right? And so on and so forth. You keep on going like that basically, right? So what you see in the end, y3 has captured the meaning of this sentence basically, based on these three words, w1, w2, w3, right? So it has extracted all the information that is relevant for this task, right? And then using this y3, you could make a prediction. So for example, you could use something called a softmax, which will take this y3, kind of map it using the weight vector w, like as you did in the like a perceptron, and then exponentiate it and normalize it to get a probability distribution. So this gives a probability of a class C given the words w1, 2, 3, right? So this is, let's say, positive, could be a class, negative, or neutral basically, right? So these three classes it predicts basically, right? Yeah, so any questions so far? Yeah, maybe you can ask me a question because I cannot see the chat actually, or I cannot see any other sign. All right, so if there are no other questions, then yeah, so basically RNN is essentially like a kind of a computer. That's another way to look at it basically. So what is happening in RNN is it is maintaining some kind of memory, this H, which we saw, and which is in form of the hidden state. And what happens is, like, this memory is being continuously maintained and monitored. And then whenever a new input comes, xi, let's say, it updates its memory, basically, right? Basically, you get a new updated hidden state. So basically, it is manipulating the contents of the memory conditioned on this input. So it's like kind of a computer which is being done, like some kind of a computation which is being done here, basically, right? So so and you keep on doing this as in when you keep getting word, right? So here you can see that these words X, I's are basically kind of instruction which RNN takes it, and based on that it manipulates the memory and produces a new memory state which can be used for giving output or could be used for further for the next step, right? So this is kind of a differentiable computer and kind of a neural Turing machine, basically, right? All right. So now let's see how RNN could be used for the same classification task that we saw earlier. So you take in this again. Take the sentence, split it into tokens, and then you take the corresponding index from the vocabulary. Take the embedding for that word, like these three embedding. But now instead of combining, taking the average, you feed this embedding sequentially one by one to the RNN, right? So as we saw this, like this one here, you were feeding each and every word one like that. You basically feed the each word one by one to this RNN. And finally, RNN gives this Y3 as the output, right? And then this is used for prediction, right? And then so this is how it looks like. You get, let's say you have n words and then you get yn, then you pass it through the MLP, and then you have a loss function as I showed earlier. This loss function measures the discrepancy between the output y hat, which is the predicted output, and the true output, and then these all this loss is used to learn the parameters of all the model via backpropagation, right? So this is how it is learning, right? So this is RNN which is used for classification, right? So you could also do little bit different. What you could do is you can use this RNN for generation as well. So for example, I want to do a machine translation, basically, right? I have this Hindi sentence and I want to translate it to English sentence, right? So how would I do it? I would feed in this the Hindi sentence word by word into RNN, right? Like I start with this SOS is start of sentence, EOS is end of sentence, right? So I start with this word Billy, and then I feed into RNN, and then I feed in all the words, and then finally I get this final representation C, right? And then this C is fed into another RNN. So these two are different RNNs, by the way, right? So this is another RNN. This is the H0 for this RNN, and then it generates these words one by one, basically, till it comes across, till it generates end of sentence. Right, so it goes sequence one word by word. So this is also called a sequence to sequence model. Right, so that's how it could be used for machine translation as well. Right, and there are different ways of doing it. Actually, I could earlier I was using C, which is fed as hidden representation H0, but I could also do is this C could be fed to each and every step, basically, right? I can at every step I combine it with the embedding. So this is embedding for start of sentence, and then I combine it with the every embedding. And one thing you to note is that here I'm feeding the word that was predicted earlier to the next step, basically. Right. So here also this is what is happening. Yeah, you're feeding this word. What you have produced, it goes as the next step. Goes to the next step, basically. Right, so and this is how you're kind of generating the English sentence. All right, any questions so far?
Sir, it is also used for a piracy check also. If we have to check a piracy check, if
Piracy check.
for any document,
Hmm.
for any
Uh,
documentation,
mm-hmm.
it can it
Hi.
can be
It could,
applicable there also.
it could be used. See, see, these are general learning machines basically. They can be used for any kind of application. So, for I guess you mean plagiarism check basically, right? So, what you could do is you can learn the represent. You can feed the document word by word and then learn some representation for that document, right? Let's say D0, and then you have the representation for each and every document in your let's say you have a corpus of these documents, right? DN. And then you compare with each and every document basically. And then if the document which is most, the vectors which are most similar, they are kind of similar documents. And then that's how you say, okay, this document is already there in our corpus basically. If these two are very similar.
Okay, sir.
Yeah, so in general, these can be used for any kind of application basically, right? All right. So then another important thing to note here is like what we were doing was that we were feeding this C or the context as it is called C to each and every step basically, right? But what happens sometimes is that when you're, let's say, doing a machine translation, right? Word, suppose I'm generating this word sat. I want to so this word will depend. I mean, it will depend on other words in the input sentence as well, right? So, for example, this might have a high correlation with, let's say, this word Billy, because Billy is something which will sit basically, right? I mean, if this was a table, then it will not, because table cannot sit. So this word would change basically, right? So what we want to do is we want to capture the importance of different words which are there in the input, or basically we want to focus the attention on certain words when you are producing this word or generating this word basically. And this is done with something called attention. So what you are doing is essentially you have these Y's, right? So you have these Y's which are generated here, right? And these are kind of a representation or the summary of the sentence so far, basically, right? So what you do is you have some weights associated with each of these Y's. And these weights you learn by measuring the current hidden state, similarity between the current hidden state and the Y, each of the Y's. So this is indexed by IK basically, right? So this is, let's say you are generating this at this particular position 2, you want to generate some certain word. So most likely cat should have very high weight for this word Billy, because cat directly translates to Billy, or Billy directly translates to cat, right? So this alpha ik, so alpha, let's say this is 2 and this k will be 2, 2 should be very, very high basically, right? Whereas alpha 2, let's say guy, which is like 4, should be very low because it has very less correspondence. Right, so these alphas are measuring the similarity between this hidden state and the word in the input on the input side, on the encoder side, right? So by the way, this is called encoder and this is called decoder because it is encoding the meaning and this is trying to decode the meaning into English sentence, right? So this alpha ik will measure the importance of different words in the encoder, and then you take a weighted sum of all of these. So these will very high, so most likely if this is very high, so y2 will y2e will have very high value and rest might be zero basically, right? So it learns to focus on its attention on different words for generating the output, right? So this is what is called as attention mechanism, right? So any questions on this? All right, so then yeah, so now this is the last bit of this deep learning crash course basically. So these are something called transformers. So these are like the state of the art architectures which have kind of revolutionized the natural language NLP field, basically natural language processing field, basically, right? So idea here is that I mean, in the RNN, what you were doing, you were going sequence by sequence. I mean, sorry, word by word, right? One word at a time, basically. So this cannot be parallelized, and hence it is slower. So what you do is, or transformers, you have some new architecture called transformers. So these are like auto-regressive sequence models, basically. So here, what you do is you don't have any recurrence here, basically. What you have is fully feed-forward attention-based architecture. And the main idea that is used is self-attention. Basically, it tries to focus the attention on. So in this one, you were focusing the attention on the words in the encoder. Basically, here what you do is you focus the attention on the word in the sentence itself, basically. Right. So and because of this is highly parallelizable, basically. Right. So for example, as I said, like RNNs are focusing attention on words in the encoder side, but in self-attention, you focus on word within the same sequence, basically, right? So for example, if you have this sentence, we went to the bank and saw a lot of people with check in hand, basically, right? So this bank, when I'm trying to look at this word check, it has a direct correspondence on this word bank, basically, right? Because check is directly related to bank, right? So if I mean, because bank can have different meanings, right? Bank can be a financial institution, but it can also be a river bank, basically, right? So this check gives a direct clue that this is a financial institution. So there is this attention where it needs to focus on to learn a good representation for this sentence, right? So this is what transformer does, basically. So here, I mean, let's look at how it does that. Let's look at the self-attention mechanism to be more precise. So you are given these sequence of words or tokens, W1 to W1, then you get the embedding for each of these, basically, as we saw earlier. And then what you do is for every word, you have three vectors associated with it. One is a keyword, a key vector, query vector, and a value vector. So the idea is that when I'm looking at a word, particular word, for example, let's say I'm looking at the word check, that is my key. So consider it's like a table, right? So you have a key in the table, right? Key and value pairs basically in the table, basically, right? So consider that as my key, and then I query. So these are each key is associated with a value. So now if I'm interested in a word check, so every word also has a query vector. So I will take the query vector of check and then compare with keys of each of the word in the sentence. And whichever has a high value, which has a high similarity, then that means word is very much related to this, and then I'll pick up the value of that. Right. So I'm kind of indexing the representation or the meaning of different words using this. Right. So this is what it is done. As I said, like you calculate the similarity, you get the key, query, and value vectors, and then you calculate the similarity or the attention weights between the key and each of the queries. And whichever the attention weight, and then you do some normalization. I mean, this is not really, I mean, this is just for kind of, no, this has importance, but I mean, right now you can kind of ignore it. So what you do is you scale the scores with, for now, maybe you ignore this thing. And then you normalize it using the softmax, basically. Right, and then you get a normalized score for each of the value vectors, and then you get the weighted value vector for each of the n units or n words, basically. And then you use this as the representation for that word, basically, right? And this is basically kind of a contextualized representation. So basically, it is taking into account the context when trying to learn the representation. Right. So, and this is what self-attention is, and this is how compactly you will write it. This is in form of matrices, basically. And so what you did was basically you did took query, key and value, and then you did certain multiplication, scaling, and then softmax, and then you get this multiply it with the each of the values with the normalized vectors, basically, right? Normalized values actually. So and then okay, I mean maybe you can ignore the multi-head self-attention for now. So yeah, so basically what you do is you can do it in multiple different ways. I have one instead of having one key query and value, you have multiple different key query and value, and each of them is giving a different representation, basically, right? Or different heads, basically. So this is how the transformer encoder would look like. Then you have, so basically you have inputs, and then you pass in to the attention mechanism, and then you do some normalization, and then yeah, basically that's how you get the Oops. That's how you get the representation for these, right? And one thing you might, similarly on the decoder side, you are basically decoding or generating every word. So you are taking the attention, you are having attention from the encoder side as well as the decoder side, both of them basically, right? And then one thing you might have noted that we are ignoring the position because we are taking a feed-forward network. So in order to take into account the position, you also have some kind of position embedding which is added to the input embedding. This position embedding is basically calculating the relative position of the word in the sentence and basically passing it through a sine function or a cosine or a cosine function to get a representation, basically. Right, so this is how the entire transformer model for translation would look like. You have the encoder, this one, and then you have a decoder, basically, right? And on the decoder side, you generate word by word, basically, right? So so transformers, as I said, they have kind of revolutionized the entire field of text processing, basically, right? So there are lots of different transformer architectures. What I showed you was a very basic one, but there are lots of different architectures which have been proposed. So one of the most popular one is this called BERT, bidirectional encoder representation from transformers. So here, in this transformer, the representations are learned in an unsupervised way by using two different tasks: mask language modeling and next sentence prediction, basically. So the idea is kind of very simple. So you take in a sentence and you mask or basically hide certain words, and then you want to predict these words given the context, basically. It's like I hide one word and then I show you the words in the neighborhood, and then I ask you what word should go there. So this is how the model learns a good representation. And similarly, next sentence prediction is you are given one sentence. Basically, you give input as two sentences, like let's say sentence A and sentence B, and then you want to predict whether sentence B follows a sentence A or not. Right. So with the help of these tasks, you learn kind of good representation for the words and the sentences. Right. And similarly, lots of other architectures have also been proposed. For example, Roberta, XLNet, Distilbert, so on and so forth, basically. So any questions so far? Yeah, so that kind of concludes the deep learning part of the lecture. Any questions? So I'm audible.
No,
right?
sir.
Okay.
Yes,
All right.
sir. No
Okay.
question.
Okay. All right. Okay. So now finally we'll go to, so as I said, like these deep learning part took a lot of time because it's quite, I mean, I said like it would take at least one semester of course to understand all these things, but I did a very high level overview to give you an idea. So now let's go to the main topic of the talk, which is affect. By affect, I mean emotion. So why should we care about affect? So let me just motivate this with the help of an example. So nowadays we have all these lot of personal digital assistants, right? Like Alexa and then Siri and all these. And many of you would be having at your home, and you would be interacting with these basically, right? So for example, I mean, there's one example interaction here. So there is this personal digital assistant, and it's at home, and then a person goes to home. So it is greeted by this assistant. So for example, it says, "Hey, buddy," and then he says, "Hey." Then it casually asks, "How are you doing?" And then obviously the person didn't have a good day, and he just kind of expresses that I had a long day, kind of very sadly. And then, I mean, the digital assistant completely misses the emotion or the affect in the affective content in what the person said, and just says, "Awesome, let's celebrate," which makes the person even more angrier. Actually, it completely misses that the person is sad and didn't have a really good day, and gives a really bad response, basically, right? So basically, this is this problem many of you might have also encountered when interacting with these digital assistants. So currently, the problem is that machines fail to understand the affects or the emotions of humans when they are interacting with them, basically, right? So what we want, what we would like to do is develop machines which understand the human emotion as well, because emotion is a really integral part of human-to-human communication. Right. So emotions are basically universal across. I mean, so emotions are all present in almost every culture and society. So these are kind of and traditionally emotions have been kind of considered orthogonal to let's say rational thinking. But recent studies in neuroscience have demonstrated that even rational thinking. That even for rational thinking, emotions are really important component, basically, right? So, and as I said, like to interact seamlessly, it is really important to understand the underlying emotions of people, basically, right? And there is a very so this person Marvin Minsky is like one of the pioneers of AI, and he was one of the early researchers who worked on the AI, who was involved in the development of AI as a field, basically. So he has written this book, Emotion Machine, and he has this quote that emotion is not especially different from processes that we call thinking. So emotions are kind of, they go beyond the surface level communication, but are indicative of the underlying thought process of the person, basically. So that's why emotions are really important. I mean, it's really important to develop machines which understand human emotions, basically. So this brings us to the field of affective computing. So affective computing is the study and development of systems that recognize, interpret, process, and simulate human feelings and emotions, basically. Right. So it is kind of a way to understand human emotion and possibly also generate these. So this is also known as artificial emotion intelligence or emotion AI. Right. And this has lots of different applications. For example, emotion recognition could be useful for customer care, where there's a kind of a bot which understands your emotion. Then it can be useful for reviews. Then it could be useful for analyzing social media data. And one interesting application could be like, it could be part of a car driving system where the system analyzes your emotions and then recommends whether you should drive or not, basically. Right. So these are some applications. There could be other possible applications also. So now this brings us to the question, why should we care about multimodal affect? So by multimodal affect, I mean like combining different modalities, for example, video, audio, text, or maybe some kind of physiological signal like eye movement, pulse rate, and all those things to predict the emotion. And so, as you might have guessed, that emotion or affect is not an isolated phenomena, right? So emotion is conveyed via different means, and then it is present across different modalities, right? So your facial expressions would be indicative of certain emotion state along with your voice, basically, right? So when you are sad, your face has a particular expression, and then your voice is also a bit different, basically, right? So essentially, the modalities complement each other with regard to the affect information, right? And now the question is like, I mean, it's good to combine these modalities, but how do you fuse the information coming from different modalities to learn a representation which can be useful for affect for prediction, emotion prediction? So here is kind of a generalized architecture for effective computing. So for example, you have a video or a input in form of a live stream, and then you have different modalities. For example, you have visual modality, like you have face and postures, and then you have audio modality with different intonation, pitch, etc. And then you could have, like, say, let's say, a text modality in form of transcription, basically, right? So what you do is you learn representation for each of these different modalities. And for example, you might have a modality specific latent representations, and then you combine, fuse them to get a joint representation. And this is fed to a classifier to predict the emotion. And one thing to note is that you also take into account the context or the history when you're, let's say you are at this particular scene or current frame. And then what you do is you will also take into account the previous frames to predict the information, right? So take into account the context or the history or to make the prediction. So this is kind of the generalized architecture, which could possibly, this is one of the possible architecture. There could be others as well, basically. Right. So any questions so far? All right. So then this brings us to the topic of emotion AI, which is what we are interested in. So the idea is to develop machines that can interact seamlessly with humans, and they should understand human emotion and also possibly exhibit human emotions, basically, right? So for example, if you had, let's say a bot or maybe like a robot which can understand your emotions but also generate certain facial expressions, basically corresponding to the emotion, basically, right? So there are two class of problems that need to be addressed. One is emotion prediction or recognition, and emotion generation, basically, right? So maybe now I'm going to go into I'm going to talk about some of our work in each of these areas, prediction and generation. Any questions so far? All right. So then let's start with emotion prediction. So, I mean, this is one of our recent works. So fine grained emotion definitions. So basically the idea here, the problem that we are trying to address is, given a sentence, what are the emotions expressed in it, basically, right? So for example, you have this sentence, my dog's name is Bruno and I love playing with it. Might be like a happy emotion. And then you can have a sad emotion, or then you could also have some kind of a disappoint or some maybe kind of a sad or maybe kind of remorseful emotion, basically, right? But one thing to notice that the words are more or less similar across different sentences, but the emotion is changing quite differently based on the how the words are written, basically, right? So a simple approach where you just take the words, like kind of a bag of word approach that I showed earlier, may not work well, basically. So now, before we go into emotion prediction, so the question is, how do we represent emotions? So emotions and there are like broadly speaking, two ways of representing emotion. One is by a discrete label, and another is continuous value. So in discrete label, you say that, let's say you have, let's say, negative emotion, neutral emotion, positive emotion, or you can have like different emotions like joy, trust, fear, surprise, sadness, and so forth. And on the continuous, the another way is you represent emotion by continuous value, where you represent an emotion by a vector of three values, valence, arousal. So there are lots of different corpora for emotion prediction that have been proposed, and they have used different representation schemes. So for example, ISAR, emotion stimulus. So what we use is something called co-emotions corpus. So this is kind of a fairly large corpus. It is annotated with 28 different emotion categories, and it has around 58,000 sentences. So here is like a sample text. So for example, you might have this sentence, oh my God, yep, that is final answer, thank you so much. So this is kind of emotions that are labeled for this, like gratitude and approval, basically, right? So as I said, like there are 58,000 sentences. Wait. So yeah, so there are 58,000 sentences, and there are 28 emotion categories, and so some of these sentences have multiple emotions as well, basically. But majority of them have a single emotion label. So here is the heat map which shows the correlation between different emotion categories. These are like different emotions, and like certain emotions are highly correlated to each other, and some are not at all correlated. So for the baseline approach, so there are like different ways of predicting the emotion. So like example, keyword based, rule based, and deep learning based approaches as well. So the baseline approach is I think I introduced this model BERT earlier, right? Which is kind of a transformer model. So what you do is you feeding the text to this transformer and you make a classification. And these are the results for this. So average on an average, the accuracy is 0.46. F1 score, not accuracy, sorry, F1 score is 0.46. So what we propose is a different model. So when you try to, so basically, yeah.
Sir, can we see the data, previous data?
Previous data, what do you mean? Like
yes,
this one?
Yes, this one. Excel sheet.
So this one, right?
Yes, sir. Yes. That Excel sheet, can we see? Data file.
Excel sheet. Which Excel sheet? This one?
Yes. This next one from this heat map is drawn.
Okay, this one.
Yes. Can we see that Excel sheet of data? Yes.
No, so okay, I will provide the link later, which you can use to get the data.
Yes.
Yeah. So basically, so when you are giving a label to an instance, right, or to a sentence, what defines that label basically, right? It's some kind of a feature. So for example, you have apples. Then apples are round. They are red in color. So this definition defines what an apple is. Similarly, oranges are kind of also round but orange in color basically, right? They're sour in taste basically, right? Or maybe kind of little acidic in taste basically, right? So basically, if we can make use of this definition itself, then it can be quite useful for the prediction basically, right? So this is what we do. We create a multitask framework for predicting the emotion basically, right? So what you do is you take in certain, so the idea of multitask learning is that you have certain tasks that you want to do, and then there are certain associated auxiliary tasks which are not the main purpose of your application, but they are related to the main task basically, right? And the parameters are shared across the task basically. So the idea is that these auxiliary tasks will help in learning better representation for the main task basically. Right. So for our case, also what we do is, other than predicting the emotion, we also predict whether, we append the sentence with the definition, and then we also predict if it is so for example this one, and then we also predict whether it's is the correct definition for the sentence or not. And similarly, we also do another thing. We mask certain words in the sentences and then predict whether this what is the masked sentence, masked word in the definition sentence basically. So this gives rise to two auxiliary tasks: class definition prediction and masked language modeling. So class definition, you given a pair of sentence, and emotion definition predict if emotion definition corresponds to the emotion depicted in the sentence. And in MLM, what you given a pair of sentence and emotion definition, some of the tokens are masked, and you have to predict the masked token basically. Right. So these are the auxiliary tasks, and the main task, of course, is given a sentence predicts the corresponding emotion. Right. So we did some data processing for this for create the auxiliary data, and this gives us to rise to like three different models where we have class definition prediction, masked language modeling, and the combination of the two. And as you can see, this helps to improve the result. This was the baseline, and this helps to improve the result. The auxiliary tasks are helping to improve the result basically. Right. And similarly for other, okay, maybe you can ignore this. And then you can see that for certain categories, there is a big jump in the prediction. So for example, this grief, it was in the baseline 0, but here it's almost 50. And then we also tried we're trying to apply the same model on other data set. And it, as you can see, it performs much better than the simple bird-based model, basically. Right. So basically, we did some analysis of the data, and then so the task itself is subjective. Like certain so annotators annotated certain emotions. For example, this sentence, it is annotated with sadness, but our model is predicting love and remorse, which is equally good emotion in this case, right? So perhaps a different evaluation strategy is required, and possibly we could make use of some kind of a taxonomy. The heat map that we saw, the taxonomy, we could make use of that information for predicting the emotion. So just to conclude this work, we propose a model which makes use of definition for predicting the emotion. And we saw that it improves the emotion prediction compared to the other models which are out there. And if you want to check out the paper, here is the link, and you can also get the code and other details on this GitHub repo. Basically, you can basically scan this QR code to get to the link, basically. All right, any questions so far?
Hello, sir.
Yeah.
Sir, how exactly the BERT works? Can you please tell me?
BERT is actually fairly complicated model. So if I go into that explanation, it will take a lot of time. But I can very briefly tell you it's a transformer-based model that we saw earlier, right? We saw these transformer architecture. So it's a transformer-based model which learns the representation for the word using self-attention. Right, so we saw long time back I showed you the BERT architecture, right? So I'm not going into detail in the interest of time, but you can check out for more explanation on BERT. If you type BERT in Google, right, you should be able to get to the paper for BERT, and then it explains that. Essentially, it's a transformer model, right? All right, any other question? All right, so then maybe I'm...
Hello, sir.
Yeah.
So, yeah. Sir, BERT is actually a encoder, isn't it? So, is it like our regular encoder?
What do you mean by regular encoder?
Regular encoder means label encoder or... See, BERT is nothing but basically bidirectional encoder representation for transformers. Okay. So basically, BERT encoder means our is it our regular encoder like label encoder or one hot encoder? Is it like that?
No, it is much more it's a bit more sophisticated than that. It basically encodes the meaning of the word based on the its neighborhood, basically. Okay. Using self-attention, basically.
Okay. Sir, one more doubt, sir. So we are using words here, or we are using sentences to identify the emotions. Am I right, sir?
No, yeah.
Yes.
So we are using, we're breaking the sentence into words and then feeding it into words.
We are doing tokenization, then we are...
Yes.
So is it like NLP itself?
Yes, this is NLP, yeah.
Okay. That means we can use the same tools that we are using for NLP, NLTK and all these things.
Yes.
Okay. I thought it's like images there, and from image...
No.
The image
no, there is no image. It's only text only, which is there.
That's why I said, can you show me that data?
Yeah, you can get more details on this. Check out this paper, actually.
Okay.
This paper has all the details, and it also has the link to the GitHub repo.
Okay. Thank you, sir.
All right, so I think I'm almost out of time. So I'll maybe very quickly go through this thing, or maybe I can skip this part. Yeah, so basically, the idea here was we want to do some kind of multimodal prediction, and what we try to make use of is, as I showed earlier, we try to make use of the video, audio, and text modalities to do the prediction. But here also we do a so we have a conversation going on between two speakers. We have a speaker specific information, like and then also we take into account what were the emotions of the speaker previously. So we try to kind of model that basically, right? So idea is kind of something coming from shapes of something called shapes of stories. So there is a very famous author, Kurt Vonnegut. So he proposed that every story has a shape which is plotted by ups and downs experienced by the characters. So for example, you look at Ramayana. So if you look at the, let's say the character Ram, so basically there are ups and downs of this character in this story basically, right? Like at some point he's happy, then sad, and so on and so forth. It is kind of varying basically. So every story has these ups and downs. So there is an emotional arc which is going on basically, right? Every story defines an emotional arc basically. So we want to make use of this emotional arc when you are trying to make predictions basically. And that's what we do in this thing. So I'm not going into too much details because I'm almost out of time now. Yeah, so I'll now quickly tell you about another work where we try to do the emotion generation basically, right? So what we try to do is given certain emotion label and certain intensity of the emotion, we generate the text corresponding to that emotion, right? So, and there also we make use of the transformer architecture. So for example, I will just give you just a second. Yeah, so here is the model. So basically what we have, let's say, we give certain prompt, let's say once upon basically. And then the model, so this GPT-2 is a transformer model which generates text. So it generates text and this beta is the intensity of the emotion. And we also tell some kind of topic. And then we, let's say, we want a happy emotion, then we give the happy emotion, emotion in form of the bag of word model. And then we generate these texts. So corresponding to different intensity, we get different kinds of text basically. Yeah, I'm kind of skipping a lot of details in the interest of time, but I will provide you the link so you can check out more details later. And the way we do it is we perturb the probability distribution of this basically this transformer architecture basically to generate certain kind of emotion based on. So we perturb using this topic and the intensity and the desired emotion basically, right? So we have two kinds of loss here. Right, and then we did perform a lot of experiments using both human evaluation and automated, and in all these experiments, the model works pretty well. So yeah, sorry, I'm skipping those details because I'm out of time. But here are all, you can find the details in this paper, and you can also find the model on this code repo basically. Right, so now maybe I'll conclude this presentation. So I showed you, I started with a brief crash course on deep learning, and then this was followed by, I explained like why effective computing is really important. And then I introduced certain models, one was for predicting the emotion from the text using the class definition. And then I introduced the general multimodal architecture for predicting emotions. And I could not go into details because of the time, but I provided you the link so you can check out these. All right, okay, thanks a lot. So any questions?
So for text recognition, so which language you used? Only English language is used, or?
But so it's most of this work has been done in English, but we are actually also looking into other languages like Hindi and all other languages. The problem is that we don't have data for these languages basically. So once we have the data, we can do it for any language basically.
Okay. Thank you.
Okay. Any other question? All right, so if there are no other questions, okay, thanks a lot. I think, so yeah, that's it from my side. Yeah.
Okay. Thank you, Dr. Ashutosh, for the interesting lecture and wonderful, lively question answer session. Participants, now you will have a short quiz, after which the link for the feedback will be shared in the group. Kindly fill it immediately. At 12 o'clock, we'll have the validatory session, so please join.